I want to start by thanking Phil and Patrick for inviting me here. I'm going to talk a bit about some very fast methods I've been working on recently for performing numerical simulations of structure formation in quite general theories of gravity, including that has like a screening mechanism. So we start with the same motivation as always, that we're in a time where we have a lot of these upcoming surveys, which one of their main objectives is to test gravity on cosmological scales. In order to do this, in order to use this data, we need to connect it to theory, and for this we often rely on perturbation theory. However, perturbation theory can only bring us so far. If we want to use the information on nonlinear scales, or quasi-linear to nonlinear scales, and to have accurate predictions, we need to rely on numerical simulations. And also for many of these future surveys, there's also a need to generate a large ensemble of galaxy mocks to model the observables, the covariances, do checks of systematic effects, etc., etc. And for this, when I say large examples, we're talking about 1,000, 10,000, 100,000 number of simulations needed for this kind of effect. And for this, n-body simulations are a bit too computationally expensive to be useful for this. So faster methods are really needed. And over the last 5-10 years, there's been a lot of effort in developing such approximate methods that can be used for this. Most of them use some form of Lagrangian perturbation theory and such. I will discuss only one of these methods, which is the so-called COLA method, the COmoving-Lagrangian-Accelerations, for doing such simulations, and how this can be extended from lambda CDM to a large class of non-standard models. And also you can use this to include massive neutrinos. So just a quick recap of n-body simulations in lambda CDM. This is like the simplest thing you can do. It's Newtonian equations. You take your dark matter density field, you generate the realization of it, and then you just evolve them using these two equations. The geodesic equation, acceleration equals force, and the force follows from the Poisson equations. This is very simple to solve, and there's a large range of codes out there that can do this for you. The main challenge in this is, well, if you look past introducing some of this additional physics that we know exists in the universe, and only focus on the dark matter part, then the main challenge is to make it accurate on a wide range of scales, make it fast, etc. But we know how to do this pretty well. So as you move from lambda CDM to general classes of modified gravity theories, not much change. For these common scalar tensor theories, the main change is the introduction of a fifth force, which has its associated field equations that you need to solve. So instead of just solving the Poisson equations, you also need to solve this field equation for your extra degree of freedom. Not that much more complicated. Main difference is that this field equation is, or rather has to be, in order to have screening, highly nonlinear and often has bad convergence properties, which makes it just a bit slower, like a factor of few slower. However, this can, in some cases, be improved so that it's only a factor of 1.5 or 2 slower than LMCM simulations. But that's not too bad. OK, so that brings me, so this is the basis for the n-body, and that brings me to this COLA method. So the idea behind the COLA method is quite simple. So if you're only interested in the large-scale evolution of the dark matter density field, so instead of solving for the full particle trajectories in your simulation, what you do is that you simply perturb it around the path predicted by Lagrangian perturbation theory. So your x, which we have here, is expanded as the Lagrangian path, if you will, and some residual. So the equations you end up solving are pretty much the same as before, except that you have this extra term here coming from the Lagrangian perturbation theory. And otherwise, it solves exactly the same as in a normal n-body simulation. And this displacement field, you can compute it order by order in perturbation theory from your initial conditions, and that's quite straightforward. So if you take, like, for the lambda CDM model, it's quite simple. This displacement field, it factors perfectly in time and space. So once you have computed this once, you know it at all other times. So, and also when you generate your initial conditions, you often use second-order Lagrangian perturbation theory, so you already know this thing. So it comes for free. So why do we do it this way? What's the advantage of doing it this way? Which is just just a mathematical rewriting of the equations, because the split is exact if you just use a large number of time steps, a small grid size, etc. But the gain of doing this is that if you're only interested in large-scale evolution of your density perturbation, it allows you to take very large time steps in these simulations. So you can rely on only like 10 n-body time steps instead of like the thousands you need in normal n-body, and still maintain the accuracy on large scales. So you say just screw what happens on small scales and only focus on the large scales. And we can also work with a fixed grid in opposed to these n-body simulations where you have adaptive resolution, and which makes it more complicated to solve, and which means you can solve everything with fast Fourier transform, which also speeds things up. So in practice, this method is often like 100 to 1,000 times faster than traditional n-body. However, it's not a replacement for n-body. It's only useful for studying large-scale clustering statistics. If you want to study how the power spectrum is up to a certain scale, regression space distortions, generation of Machs, etc. You wouldn't use this if you want to study internal halo dynamics or small-scale dynamics in general. So that was the COLA method so what I discussed here, this is the COLA method for lambda CDM. So as you move to more general theories, it becomes just a bit more complicated. So in general, the growth of linear perturbations are determined by like an effective Newton's constant. Can be other things also, like frictions terms and stuff, but I'm just going to focus on the simplest case here, which often is scale dependent, which again leads to scale dependent growth factors. And to generalize COLA, we need to just figure out how to add support for this. And also, as I said, these COLA simulations are pretty similar to normal n-body simulations. You do exactly the same apart from this split. So you also need to solve for this additional degree. You need to solve this field equation for your extra degree of freedom. The way this is done in traditional n-body codes is like using, I forgot the name. Relaxation methods, that's what I was thinking about. Yeah, and this is a bit too slow if you want to have this huge speed up, which is what makes this method good. So in order to do this, we need another approximation here is to figure out the way to solve this field equation fast and accurate. And for this, we use a fast approximate method that we developed a few years ago. So what do we know about how the solution to, for a lot of these modified gravity models, we know a lot about how this solution to the field equation behaves in certain regimes, at least two regimes here. So we know on large cosmological scales, you can just linearize your field equation. You end up with this linearized equation, which is easy to solve. However, using this in simulation, that's one option. However, it's not good enough, as it misses the main ingredients of this modified gravity model, which is a screening mechanism. However, we also know how the solutions behave for spherical symmetrical configurations. There you can almost solve it analytically or semi-analytically. And the result one typically find is that like the fifth force is just some strength times the Newtonian force amended by some screening factor, which you can compute, which depends on theory from theory to theory. So what does this screening factor really tell us? Well, it tells us how much of the local matter density contributes to this fifth force. And it usually depends on quantities that we know, like the Newtonian potential, the gradients, or the second, or the Laplacian of it, which is just the density. So the proposed method we put forward a few years ago is that instead of solving this horrendously nonlinear complicated equation, is that we instead start with the linearized equation, and then we amend to it a screening factor that is computed from looking at spherical symmetric configurations. So like if you have like an f of r gravity, this epsilon would just be something like this. And if you have like a DGP model, you would have something like this. Of course, this is just a purely phenomenological way of doing it. So you have to test it and see how well it does by comparing it to proper n-body simulation. But it has some advantages. It agrees on linear theory on the larger scales, and it models the screening effects on nonlinear scale. Another advantage is that it's a completely linear equation in phi, so it's much easier to solve. You can use fast Fourier transforms and solve it just as easily as the Poisson equation. So a few years ago, we implemented and tested this in traditional n-body codes for several different models. Here's just like just a quick, just some example plots of that. So this is for like an f of r gravity. This is for a Galilean, I think. Not totally sure. But the main thing here is just the enhancement of the power spectrum relative to lambda CDM. Here shows you what you get if you just use a completely linear field equation. And the red one is you solve it exactly, and the green one is what you get with this method. And for all these years we tested it, you get like percent level agreement in the matter power spectrum and also in the halo mass function, to at least for the highest masses for a wide class of models. And also another advantage is that it often gives conservative results. So instead with a linear, using a completely linear thing, it always overpredicts the amount of clustering. Here it often slightly underpredicts it. So this shows that this method works pretty good at approximating the solutions to this, in general, very complicated field equation. So this is the first ingredient we need. The second thing is just how to compute this displacement field in order to use this in a COLA simulation. So as I told you in lambda CDM, the main advantage there is that you have time-dependent growth factors. So this displacement field perfectly factors in time and space, which is a huge advantage for you only need to compute it once. If you go to general theory where you have scale dependence, it's a bit more complicated as it doesn't factor in configuration space, but it does factors at least the first order in Fourier space. So instead of having one growth factor, now you have one growth factor per K mode. But that's not too bad because it's easy to compute and store and then get this displacement field. Well, if you go to second order, it becomes much more complicated. If you wanted to factor, you need to you get the second order displacement in Fourier space is given by this horrible convolution integral, which if you want to solve this in a code every time step, you're screwed. So what we do here is that we rely on an approximation. We basically assume that this has the same K1, K2 dependence as you have in lambda CDM, and then you end up with like a very simple equation for the second order growth factor. And it turns out this doesn't matter that much for the result. So this is a fine approximation. So with this approximation, what we do is that we once you run your n-body your COLA simulation, and you need to have this displacement field at every time step. So what you then do is that you basically get them from computing these growth factors and taking a Fourier transform with respect to the initial displacement field they computed. So this is a bit more computationally involved than in lambda CDM, and which makes it roughly 3, 4, 5 times slower than COLA for lambda CDM. However, this is still a huge speed up compared to traditional n-body. And for many of these models, it turns out that another approximation you can do further to get away from this is just use time-dependent growth factors. Basically, you use the small k limit of the growth factors from your theory. And that turns out to be a pretty good approximation in many cases. And then you completely you don't have to do this. So then the only thing you have to do in this method is compute this equation. So yeah, earlier this year we implemented this in one of these COLA codes that's on the market and tested this against full n-body simulations. And here is like some sample results of what you get. So this is enhancement of like a mass of the halo mass function, and these are enhancements of the matter power spectrum relative to lambda CDM. Both of these things computed within each code, full n-body or in COLA. And
which one's which?
this is the halos, and these are the power spectrum.
No, I mean, which is the COLA and which is...
Oh, sorry, yeah. So the red lines in each of these is full n-body. And these other lines here is, so the red and the black versus these other lines. So as you can see from this, so if you look at just the pure mass function or the pure power spectrum, say the pure power spectrum might start, for these type of simulation, for the simulation details used here, it starts deviating from the n-body around like 0.5 or something like that, k of 0.5. However, these boost factors, both computed within each code, they remain accurate to percent level up to k of a few. So this works very good, and you can apply this to practically any of these models that have screening. All you need to do is compute, of course, compute these growth factors, and you need to compute this equation here. So basically a linearization, and then you need to add your screening factor.
The class you were showing before, they were going to much higher k, k of 10 or something like that.
What? Yes, yeah, because both of these were computed in normal n-body, both of these predictions here.
Oh, that's not correct.
Yeah, exactly. So let's see. So, and of course, this doesn't just have application within modified gravity models. You can also apply the same formalism to massive neutrinos. We know that the neutrinos have mass, and they affect structure formation significantly, well, if the mass is high enough, though, on these quasi-linear to nonlinear scales. And neutrinos have this effect that they reduce clustering on small scales. So if you have a cosmology of massive neutrinos, you also have scale-dependent growth factors. So it fits very well into the same picture as we had above. Okay, the way we implemented this is that we take these things computed from CAM or something like that. This is just a sketch of how this effective Newtonian constant works in this with massive neutrinos. Also, if you're interested in modified gravity, taking massive neutrinos it's even more important than lambda CDM, I would say, as they are highly degenerate with this. In many cases, they're highly degenerate with the modified gravity signal. So this type of thing explains how you compute the growth factors. But in order to have since such a COLA simulation is just like a normal n-body, you also need to have neutrinos in the code. And that's expensive, so we also set an approximation here. So what we do is we use one of these methods that were proposed a few years ago, where when you generate your initial conditions for your CDM, you also generate your initial conditions for your massive neutrinos, which is basically they're in phase at the initial time. And as these are the Kodak matter is evolved freely, the massive neutrinos are kept in Fourier space during the whole simulation and just evolve linearly using growth factors. And this, well, this is an approximation, but it turns out to be pretty okay, at least for neutrino masses less than something like 0.6 eV or something like that. So, and here's just some results we have from implemented this in our COLA code, where here you have the power spectrum for a cosmology with massive neutrinos relative to cosmology where massive neutrinos, the mass is 0. And we have compared this to full n-body simulations. And it seems to work pretty well. We are able to get really accurate results. And we get the same type of agreement when you go to combine simulation of both massive neutrinos and massive neutrinos and modified gravity. And I guess my time is up, so I'll just put up the summary here. So that's the thing. We have extended this COLA method from lambda CDM to quite general classes of model. And it seems to work almost just as well. And we can do this almost with just a factor of few slower than for lambda CDM. But as I said, it's still a huge speed up compared to n-body. And this is very useful for many purposes if you're interested in large-scale clustering statistics, power spectrum, RSDs, etc. And it's especially if you just want to compute like boost factors with respect to lambda CDM, how much does my modified gravity theory enhance stuff, then this is also very useful for this. And well, we have put the code online if anybody is interested. And it has a lot of common models, a large range of common models implemented, and it does a lot of this analysis on the fly. So if anybody's interested, it's really easy to use. So if anybody's interested, it's up there. That's it. I'm done.
It seems to me that the scale at which the simulation starts to be inaccurate can't be very easily predicted from the start, also because it's probably model dependent. Can you comment on this?
What do you mean, when?
Yeah, like the scale at which the simulation starts to be inaccurate. You don't know it a priori if you start.
No, this you have to test against things. But there are so many moving parts involved here. First of all, like how big is the grid size you move on? How many time steps do you choose to take? These are like free parameters that will determine this. But you will have to test that against n-body in order to figure that out. I don't know any. What?
Yeah, but if I need to do n-body in order to know if the simulation is correct, then what's the point?
Because you only need to run one of these. Like if you want to determine that, you compare that to one n-body simulation, and then you can use this to run 1,000. That kind of helps.
Hans, does this really probe the nonlinear regime of the theory in the same way that n-body does?
What do you mean probed?
In the n-body simulations, you can see the nonlinear terms kicking in as compared to, say, linear perturbation theory.
Yes.
As we saw in our rather long simulations.
Yes. Well, it does in some sense. So what is this? So what is this real? There's a lot of approximations going into this, and it's basically tuned in order to. It basically works so that it gives at least clustering statistic correctly. That's all I can say. I wouldn't say that. I wouldn't use this for probing modified gravity on small scales. I'm not sure if that answers your question.
Sort of. And the other question, have you looked at how this compares with the semi-analytic approximation that Patrick and Philippe have? I mean, Patrick seems to calculate a whole pile of terms analytically, yes. And then, I'm not quite sure, does some sort of numerics, I think, yeah. In camouflage, which seems to me to be a much less computationally heavy way of doing it, but perhaps calculationally more tedious perhaps, or long? Well, I keep thinking that we can't just do n-body simulations every time we want to look at the predictions for halo masses, large-scale structure clusters in modified gravity theories. We're doing it all the time. It takes yonks of computer time. Yes. And we can't keep doing it. So how does this COLA compare, say, with what Patrick and Phil did?
Well, that's less. I would guess that's much less computationally expensive. Well, Patrick should answer that, but that's.
I don't know. I didn't compare with this, but I assume this should be maybe more accurate on I mean, it's partly based on simulation, so it should be more accurate than.
But it all depends on scales you want to go to, and also depends on what you want to compute. Say,
I mean, what would be interesting is if you could apply your method to the camouflage model that Patrick did and just see the results, actually.
well, that's easy. I already implemented that.
But actually, I'm not sure this would apply to camouflage, no, because the screening, the your epsilon assumes some kind of chameleon type screening, no?
No. You can implement that. So for camouflage, this would be a function of the gradient phi, right? So like this would be an f of x, and x would be basically this term. Similar type.
I'm not sure, but we can discuss that.
Yeah. Well, I have that in the.
Okay.
Well, I can show you the paper.
Yeah. Any more questions? Okay, then.